This is Matt Dean with A Plus College Ready, and today we're going to work some electrostatics practice problems. We're going to start with some short answer questions. What happens to the electrostatic force when the distance between two charged particles is doubled? Well, we have to use Coulomb's law to guide our thinking here, which is F, sometimes you'll see it written as Fe, equals K, the Coulomb's constant, times charge 1 times charge 2, all over the distance between the charges' centers squared. You may see that written as R squared or D squared. So we want to know what happens to the force when the distance is doubled. So if we double this R, we've got to square it. So 2 squared is going to give us a 4 on the bottom of the fraction. I hope that tells you that the new force is going to be 1/4 of the original force. Remember that Coulomb's law and the law of universal gravitation are both inverse square laws. The magnitude of the force varies inversely with the square of the distance between the object's centers. 2 wants to know what happens to this electrostatic force when the distance is reduced to 1/4 the original distance. So again, we can use Coulomb's law to guide our thinking. So this time the new distance is 1/4 that original distance. We've got to square that 1/4. So that's going to give us 1/16 on the bottom of our fraction. Well, when we simplify the fractions, that 16 is going to flip up to the top. And that should tell us that the new force is 16 times the original force. The last one, F equals K Q1 Q2 over R squared. We want to know what happens to the force when the charge of one of the objects is tripled. So let's just multiply Q1 times 3. And the distance between the charges is increased by a factor of 2. So let's put a 2 here. Don't forget to square that 2. So that 3 on top is going to increase the force by a magnitude of 3. And that 2 on the bottom is going to decrease the force by a magnitude of 4. 2 squared. So the new force is going to end up being 3/4 the size of the original force. So let's move on to multiple choice question 1. On multiple choice 1, here's what we have. So we have 2 isolated electrically charged particles. One is plus 2Q, one is negative Q. They're located 4 centimeters apart. That's from center to center. And we want to know if F is the magnitude of the force acting on the negative Q charge. What's the magnitude and direction of the force that acts on charge plus 2Q? First of all, the Coulomb's law force acts on both charges at the same time. It's a Newton's third law kind of thing. If this charge pulls or pushes on this one pulls or pushes with equal magnitude but opposite direction. So the magnitude of the force on both charges has to be F. Now, what tells you the direction is that these 2 charges have opposite signs. This one's a positive, this one's a negative. When Coulomb's law gives you charges with 2 opposite signs, the Coulomb's law force is going to be attractive. So the plus 2 charge is going to get pulled toward the negative 1 charge. So our answer here is going to be B. The magnitude is going to be F, and that force is going to be pulling that charge toward the negative Q charge. All right, let's move on to question 2. Question 2, we've got 2 metallic spheres, both of charge Q. The charges are separated by a distance of D. Again, that's center to center. The force exerted on each sphere by the other sphere is initially F. If the charge on each sphere is cut in half and the distance between the spheres is doubled, the new force on each sphere will now have what magnitude? So we're saying, again, use Coulomb's law. We're going to cut charge 1 in half. We're going to cut charge 2 in half. And we're going to double the distance. Remember, we have to square that distance. So the 2 halves on top are going to end up decreasing our force by a magnitude of 1/4. It's going to be 1/4 what it originally was, according to the change on top. The 2 on the bottom is going to decrease it to another 1/4. So if we simplify 1/4 on top divided by 4 on bottom, that gives us a change to 1/16. So our answer here is that the new force is going to end up being 1/16 the size of the original force. So we're looking at answer C. Moving on to question 3. 2 spheres, initially uncharged, are mounted on insulating stands, as shown in the diagram. A positively charged rubber rod is brought close to, but does not actually touch sphere 1. Sphere 2 is then allowed to make contact with sphere 1 on the side opposite of the rubber rod. After a brief period of time, sphere 2 is moved away several meters from sphere 1. The rubber rod is then moved away from sphere 1. What are the final charges of the 2 spheres? All right, this positive rod is going to attract electrons from X over toward this side. When sphere 2 touches 1, this side of X is going to be positive, so it's going to attract electrons from Y over to it. And those are then going to get attracted over toward the rod. So the net effect is electrons are going to move from Y to X and then over to this side of X. Then when we move them apart, Y is missing some of the electrons it initially had. X has gained some electrons. So X is going to have an excess of electrons, therefore be negative. Y is going to be missing some electrons that it had to begin with, so it's going to be positive. So our answer here is going to be B. Let's move on to question 4. When a negatively charged rubber rod is brought near to but does not touch the electrically neutral electroscope, the gold foiled leaves spring apart as shown in diagram A. We see that happening here. When the electroscope is then touched by a student, the leaves collapse as shown in figure B. You see those leaves are collapsed there. When the student's finger and the negatively charged rod are moved away from the electroscope, the gold foil leaves move apart again. We see that happening here. The charge on the gold foil leaves is, well, here's the thing. This negative rod, when we put it close to this electroscope, it's going to repel the electrons from up here down to those leaves. And those leaves separate because they both have excess negative charge. So in A, those leaves are negative. In B, when the student touches the electroscope, the student's grounding it, which means some of those extra charges are going to be repelled into the student and out of the electroscope. So the electroscope is losing negatives. That's why the leaves go back together. The negatives that were down here have now moved into the student. When the student moves the finger and the rod is moved, the leaves go apart again because here's the thing. The electroscope is now missing charges. Electrons that it used to have aren't there anymore, which means there's an excess positive charge now. And that's why the leaves go apart, because now both leaves are positively charged. Positive charges repel each other. So our answer is it's negative in A, positive in C. So that's going to be choice C. All right, now we're on question 5. 2 particles with a charge of plus Q are fixed at the bottom corners of a triangle which lies in the plane of this page. So here and here. A negative test charge of negative Q is placed at the top corner of the triangle. What is the direction of the net force on the test charge due to the other 2 charges? Well, here's the thing. This charge Q is pulling this way on negative Q. This charge is pulling this way on that one. The charges are the same. They're the same distance from negative Q, which means that we could break these charges into 2 components. Something like this. This charge is pulling down. It's also pulling to the left. This charge is pulling down. It's pulling to the right. This left component here and the right component here are equal in size but opposite in direction. They cancel out. These 2 down components actually add together and double the downward force. Point being, the net force acting on negative Q is going to be downward. It's going to be attracted to the positive charges, and that's answer B. All right, moving on to 6. When two heavy charged spheres are located a distance d apart, the gravitational force between them has a magnitude of F. So here are our spheres. Again, they're distance d apart. When the distance between the objects is increased by a factor of 3, the magnitude of the gravitational force between the objects becomes F over 9. Did the electrostatic force between the objects also decrease to 1/9 its initial magnitude due to the change in position? Well, what you've got to remember is that the law of universal gravitation looks like this. G times m1, m2 over r squared. When we increase this distance by a factor of 3, that 3 becomes squared, and the gravitational force is now 1/9 of what it originally was. Remember that Coulomb's law looks almost just like that. It's also an inverse square law. So when this distance becomes increased by a factor of 3, that 3 gets squared, and the new force is 1/9 of the original force. So the answer is yes, and it's because they're both inverse square laws, which is essentially what choice B tells us. All right, here's multiple choice question 7. The centers of two electrons are fixed a distance r apart. The electrons exert both a gravitational force and an electrostatic force on each other. Which of the following correctly compares both the magnitude and the direction of the gravitational and electrostatic forces? So here are our electrons. Remember, electrons are negative. The gravitational force, anything with mass is going to attract anything else with mass. So the gravitational force is going to try to pull these two objects together. It's attractive. The electrostatic force, on the other hand, since they're both negative, is going to be a repulsive force. It's going to try to push them apart. So we know gravity is attractive, and in this case, electrostatic is repulsive. So that means we either got to have answer A or answer B. Now here's the thing. Remember, our two equations for gravitational force and electrostatic force look almost identical. But what's different is the universal gravitation constant and K. K is equal to a factor of 9 times 10 to the 9th. Whereas G has a value of 6.67 times 10 to the minus 11. Because K is so much greater, a factor of almost like a magnitude of 20 times greater than G, the electrostatic force between charged objects is almost always going to be much greater than the gravitational force. So what that's telling me is that the electric force is going to be bigger than the gravitational force. So I'm looking at answer B as my correct answer. All right, let's move on and look at questions number 8. Two identical metallic spheres are charged to 2 plus 2q and negative 4q. And they're separated by a distance d. The magnitude of the force of attraction on the left sphere is F1. After the two spheres are made to touch and then are reseparated by a distance d, the magnitude of the force on the left sphere is F2. What is the charge on both spheres after they touch? When you touch two identical spheres together, they're going to equally share the charge. So the way to work this problem is just to take plus 2 plus minus 4. Add those together. Plus 2 minus 4 gives you negative 2. And that charge is going to be divided amongst two spheres. So you're going to go the negative 2 total charge divided by 2. So each sphere is going to end up with a charge of negative q, negative 1q. So we're looking at D. Let's go on and do number 9. Similar question, same idea. This time, we want to know after the two spheres are made to touch and then reseparated by D, the magnitude of the force on the left sphere is F2. How do the magnitudes of F1 and F2 compare? All right, so what we ended up doing, we started off Well, let's write out what we started off with. So for F1, we had a situation where we had K times plus 2Q times minus 4Q all over D squared. For F2, once we let them touch, now we have K times negative Q times negative Q all over D squared. What I want you to see about these two equations is that they have in common K, D, and Q, or Q squared. So I'm just going to call that quantity K, Q squared over D squared. I'm going to call that just X. So if I do that, I can rewrite this equation as negative 8X. And I can rewrite the equation on top as plus X. So what I'm hoping that tells you is that F1 is essentially 8 times bigger in magnitude than F2. All right, so let's look at the free response question now. So we have 3 particles that are fixed in place in a horizontal plane as shown in the figure above. Particle 3 at the top of the triangle has a charge of 1 times 10 to the minus 6 coulombs. And there's an electrostatic force on it due to the other 2 charges that pushes entirely in the negative X direction. The magnitude of the charge Q1 on particle 1 is 4 times 10 to the minus 6. And the magnitude of the charge Q2 on particle 2 is known to be of 1 times 10 to the minus 6, but their signs are not known. Determine the signs of Q1 and Q2 and indicate the correct signs below. All right, since the net force acting on Q3 is completely in the X direction, here's what we got to think about. This force is going to have to be positive. Q2 is going to have to be positive because it's repelling Q1. It has a component that's pushing this way, and therefore it would also have a component that was pushing up. Q1, on the other hand, it has to be negative because it's attracting the force. It has a component that's pulling in the X direction. It also has a component that's pulling down. So the horizontal components of both of the forces add together. The negative component, downward component here, and the positive component here cancel out. That's how we end up with a net force in the horizontal direction. All right, let's move on to B. On the diagram below, draw and label arrows to indicate the direction of the force F1 exerted by particle 1 on particle 3 and the force F2 exerted by particle 2 on particle 3. All right, well, here's particle 3. Here's particle 1. Since particle 1 is negative, the force it's going to exert, since this is positive, it's going to be an attractive force, so it's going to go in that direction. On the other hand, force particle 2 is positive. And since it's positive, it's going to be pushing away, and it's going to push away in this direction. Part C, we want to calculate the magnitude, F, of the electrostatic force on particle 3. All right, to do that, we're going to have to calculate the Coulomb's force between particle 1 and particle 3, and also between particle 2 and 3. So for particle 1 and 3, we're going to say F equals K. I'm going to leave off the units on this just to make it not as messy. That's K, 9 times 10 to the 9th, times Q1, 4 times 10 to the minus 6, times Q3, which is 1 times 10 to the minus 6, all over the distance squared. All right, we calculate that out, and that comes out to be 2.25 times 10 to the minus 3 newtons. We need to do the same thing for the force of Q2 on Q3. So F equals K times Q2 times Q1 all over the distance squared. The distance there is 3. And that force comes out to be 1.7 times 10 to the minus 3. All right, so what I need to do now is I need to add these two forces together. The problem is they're acting in different directions. They're vectors. So what I'm going to do to add them together is, first of all, I'm going to break them into components. So this top one is a force that's acting between Q1 and Q3, and it is acting, it's being pulled down. So we're going to have a force. Let's say this is our normal line. Let's erase a bit there, maybe not. So that force is getting pulled like this, where we have an angle. Let's try that again. All right, so now I have my picture drawn up a little bit better here. So that force is pulling from 3 down toward 1, down in this direction. The angle between our line and our horizontal is a 37-degree angle. So I'm going to make this into a triangle. The force is 2.25 times 10 to the minus 3. Well, what I want to do is to break that into an X and a Y component.